Welcome to Acid-Base Chemistry Part 3. This video tutorial will focus on the concept of the Bronsted Lowry definition of acids and bases, and that creates the concept of conjugate acid-base pairs. These concepts are really important to our studies, so let's get started. Alright, so in a previous tutorial we learned about Arrhenius' definition. Bronsted and Lowry came up with a slightly different one. They agreed with Arrhenius that an acid was a proton, hydrogen ion, donor. And so we've looked at those forms. We have our inorganic acids or the organic acids. Right? So inorganic and organic, right? Organic is for carbon. But then, where Arrhenius just talked about the acid, Bronsted and Lowry talked about the base as well. And we saw this in the previous tutorial, that the base was a proton acceptor. And so when we recognize bases, we see a metal, oops, that's not what I wanted, with hydroxide, or we could have amines. Okay, so now let's look at the implications of the Bronsted-Lowry definition. Basically, it says that H+ does not actually exist in water, that if the proton is donated, some chemical species must accept it. All right, so let's look, for example, at hydrochloric acid. When we put that into water, it's a strong acid, so we'll use a full reaction arrow. Then we would say that this is the acid, so it's the proton donor. And then the water is going to take the role of the base, and so it's the proton acceptor. And so then we would show that we would have H3O plus Cl minus. So H3O plus is described as a hydronium ion. And then of course we have the chloride. So the main thing to keep in mind here is that not everybody is going to pay attention. And I don't know why I put that in concentrations. We'll get rid of that, right? So when we talk about hydrogen ions, it's the most correct thing to say that they're hydronium ions, right, in water. So you want to be aware of this, though, because when you're reading information, not all authors are pay attention. So you really want to be able to interchange these. When we are in water, the most correct representation will be H3O+. But don't be surprised if you see H+ written. So this is where you bring in your chemistry understanding to fill in the gaps. So the second implication of Bronsted-Lowry definition of acids and bases is this whole idea of the proton transfer. And this idea of proton transfer creates the idea of conjugate acid-base pairs. All right, so conjugate acid-base pairs are chemical species that differ by one proton. Alrighty, so let's look at an example of this reaction. We'll use a sample reaction to illustrate this concept. For example, if we have the dihydrogen phosphate ion, and it reacts with water, and this is a weak acid, so we'll use equilibrium. So the dihydrogen phosphate is taking the role of the acid, and the water is taking the role of the base. And we know that because when we look at the products, I probably should have written that first. There's our reaction. Okay, so how did I know this was the acid? I know this is the acid because when I look at the products, I see that it lost a proton. So we would describe the dihydrogen phosphate as the acid and the biphosphate as the conjugate base. So these would be a conjugate acid-base pair. Now, so it's all of these terms, acids and bases, conjugate acids and bases, they all sound similar, but they're very different. So when we talk about the acid and the base, we're looking at the reactants. We say this is an acid-base reaction because we have an acid reacting with a base. The dihydrogen phosphate and the biphosphate, those are one of the conjugate acid-base pairs. The water is serving in the role of the base, so then the hydronium ion, right, they differ by one proton, so we would describe the hydronium ion as the conjugate acid of water. So this would be our second pair of conjugate acids and bases. All right. So there we recognize it in a reaction. To build your skills, let's, now that you have a context for the definition of conjugate acids and bases, let's see here. Let's write the conjugate base for carbonic acid. So anytime we're going to write the conjugate base, we take away one hydrogen ion. So if we have carbonic acid, the conjugate base would be bicarbonate. If we're writing the chemical formula for the conjugate acid of a substance, we're going to add one hydrogen ion. So for this, this anion right here, it would become H2S, hydrosulfuric acid. So, yeah, so that finishes that page. And now let's have you practice these concepts. So this is pretty much the main points of the Bronsted Lowry definition in conjugate acid-base pairs. So let's take some time to practice that before you get started on your homework. Alrighty, so for each of the reactions below, and this is a good time to stop the video if you want to test your understanding and then start it back up again. Alright, so we're going to label each reactant as an acid or a base. And then we're going to label each product as the conjugate base or the conjugate acid, right? Recognizing that these create the conjugate acid-base pairs, all right? So then there's the arrows connecting them too. All righty, so we look at the reactants and the products noting change. So here we see the loss of a hydrogen ion. So this is losing hydrogen, so this is the acid and the conjugate base. If this is taking the role of the acid, then it makes it very straightforward. The water is taking the role of the base, and then it accepted the proton to become the hydronium ion. So there's our conjugate acid. So we would describe this as an acid-base reaction, and we've identified the conjugate acid-base pairs. All right, next example. So look at the reactants and the products to look for change. Here we see the bicarbonate ion has lost a proton to become carbonate. So as the proton donor, we call it the acid. And then this, since these differ by one, this would be our conjugate base. since the bicarbonate has taken the role of the acid, the water has no choice other than to be the base. And we see it is the base because it's accepted a proton. And so we see the conjugate acid as hydronium. And so this would be our second conjugate acid-base pair. Okay, one last example before you get started on your homework. Now we look here and we see, ammonia, it's gaining a proton. So ammonia took the role of the base. It accepted the proton, so the ammonium ion would be the conjugate acid. All right, so here's one pair. And the water, we see, the water acted in a role as the acid this time. It donated one of its protons to the ammonium, and so the hydroxide is the conjugate base. And so here is our second conjugate acid-base pair. So we have an acid-base reaction, and we have conjugate acid-base pairs. Alrighty, so that concludes our tutorial on the Bronsted Lowry definition of acids and bases and the idea of conjugate acid-base pairs. Please take a little time right now to work a few homework problems to reinforce your understanding.